Yo, what's up? Today we're working on my custom operating system slash kernel written in Rust. This is an x86 operating system that right now doesn't do much of anything. So let's just pop it open real quick. It's called StreamOS because I'm developing on Stream, and like, why does this exist is for fun, I guess. No reason other than that. Right now it doesn't do much. It basically just has like memory allocation, and maybe that's it. Oh, and it prints to the console and it prints to the VGA device. So here is like a quick little demo of what the OS can do. So this is a console output from QEMU. Mapped into like a COM0 or COM1, I should say, in the OS. And here we can say like, oh look, we can initialize a vector, we can initialize a hash map, we can read and write the time, and we can like kick ourselves out. And so if I go into main here and I disable this IO exit, we should see, oopsies, we should see the same thing in like the VGA terminal for the viewport, I guess I should say. I don't know. Yeah, and that's where we are. And today what I wanted to do is implement CPU interrupts. So yesterday we got pretty far here. We set up the real-time clock and we can reframe it. And the goal was to be able to get maybe like a timer running in an interrupt so that we can like have like a atomic that we can look at that's like the current time or something. And where we got stuck is that the OS dev wiki said that interrupts require implementation of the GDT, where GDT stands for global descriptor table. And so it's like, okay, what the hell is that? And I got kind of stuck there. But we can start reading through. Hold on, I've got too many windows open here. I finally popped open the x86 manual from Intel, and it turns out reading docs maybe sometimes helpful, right? And this is one of those times. And so it looks like what happens from this diagram in the system architecture is when an interrupt is loaded, it asks for a segment from the global descriptor table. It's like, what the hell is a global descriptor table? And somewhere in here, it says that all memory accesses go through the GDT. Aha, here we go. Global descriptor tables. When in operating protected mode, which we are, the bootloader puts us into protected mode by default, which is just like 32-bit x86 mode. All memory access passes through either the global descriptor table or an optional local descriptor table. So we don't have a local descriptor table, but we do have a global one. And if I look at the memboot spec, I think it's called? No, multi-boot spec, sorry. Which is what Grub and QEMU are initializing my OS by. If I scroll down here, it says that there are segments that are already initialized. However, this specific thing may be invalid. So the OS image must not load any segment registers. So first we need to set up our global descriptor table and then update the pointers to the different segments, etc. That's my understanding right now. Okay, so like, what is it? As far as I understand, all the GDT is for setting up like memory permissions for different spaces. So you can imagine that when we switch between user mode and kernel mode, we might want to say like, hey, in user mode, don't just poke kernel memory, right? That's obviously a permissions problem. And so what we do instead is we say, hey, when we go into user mode, this is like the physical address range, or sorry, paged address, linear address range, I guess we should call it, as I think that's what I've seen it called, which is post-paging address range, but like not virtual, I believe, maybe still virtual, not sure. Anyways, this is like the address range you're allowed to access. And if you try to access this other range, then we're in trouble here. So like, do I have an example here? Not really. This gets like kind of complicated because we don't, in 64-bit, they actually don't use the GDT to enforce permissions. They use memory paging to enforce permissions, and so they just have like overlapping regions of GDT that just say like, yeah, the whole space is like executable, and it's also read-write, but they still have separate like data and code permissions. Not really sure why. Maybe because the OS, or like maybe because the CPU doesn't like read, write, execute, doesn't like executing writable memory. Maybe, not sure. And so what I've seen kind of suggested maybe is I could set up a descriptor that just says my whole thing is read write. Oh, I completely missed an important piece here. There's this concept of like read write versus execute. R, W, or X, I think they call it. Or like, how do you say it? How do you call this? Read write not executable. Okay, I can't really find, or is it like write or execute, maybe? W, X, or W or X. Write, X, or execute. W, XOR X. So this is basically saying that you shouldn't have code segments that are both writable and executable at the same time, because a virus or something could like modify your code, and then you'd be running invalid things. So generally they say like you can either write to somewhere, so like normal RAM that you hold like static variables in or whatever, or you can execute it. And so maybe I think that like looking at how people suggest setting this up, that the GDT is like one way that you could implement that at like the hardware level. But we don't care, right? We are in ROS, and ROS doesn't have a user space. Everything's being executed at ring 0 for now. So I think for now, we can probably get away with setting up overlapping read, write, and execute sections. Oops, this is running off the edge. And then we can, that's like probably like the simplest approach. And what I think we can probably do is we can probably like read existing descriptors from multi-boot loader, and maybe we can just reuse those for our table because we don't really care. So once we have the GDT up, then we can start looking at like pointing interrupts to that specific part of the GDT and like implementing like interrupt vectors and stuff. But the first thing to do is like set up a GDT and make sure that we understand it. And maybe we can like prove that we understand it correctly. And we could probably do this by banning writes somewhere and seeing if like our thing crashes. So by banning writes to some area. Okay. So let's start with that. Where is the explanation here? So from what I understand, there's this GDTR register, which you can just call like a load instruction into, and you can like stick this table in where this table just has like every 8 bytes. No. Yeah. Every 8 bytes, sorry, this hex threw me. Every 8 bytes, you have like a new segment. And these segments have, hold on, gotta open this guy. Have this format where they basically say like, here is my start, I think. Here's how long I can move. So this like these two parameters basically specify like the range, I think. I don't really understand what's going on here with this base. Oh, base is a 32-bit value and limit is a 20-bit value. So they're like split over like 16-bit ranges at the bottom and then like kind of like just shoved into here. So I guess this goes, base is here and here. So bits 16 to 39 and 56 to 63. Okay. Then the limit is the maximum addressable unit either in 1 byte units or 4 kilobyte pages. If you use page granularity to set the limit, then the segment will span the full 4 gigabyte address space in 32-bit mode. So this is probably what we want, because we don't actually want to have the GDT enforce anything, but maybe we'll like put this down a little bit just to see if we can like force some sort of poor behavior. Then we have to set the access byte, which is defined here, and the flags, which are set, are defined down here. So this is G flag is that page size byte that we're talking about, page versus byte thing that we're talking about, size flag. So here we just want this to be 1. Long mode code flag. And we are not in long mode because we are in x86, so we don't have 64 bits. Okay, let's look at this access byte. So present of allows an entry to refer to a valid segment. Must be set to 1 for any valid segment. Okay, so we set this to 1. Descriptor privilege level field contains a secret. So here we're just going to be 0 because we're ring 0. Descriptor type bit. If clear, the descriptor defines a system segment. Otherwise, it's a code or data segment. So what is kernel code a data segment? Let's see what it says here. I guess we'll have to like reverse engineer from this. But probably it is not a system segment. System segments are task state segments or local descriptor tables. So no, we're not even looking at these. Oh, an aside here. I was looking at these task state segments. I was like, what the hell is this? Let's see if we can pull it up here. Task state. So it defines the state of execution for a task. It includes the initial state of general purpose registers, segment registers, EIP registers, segment selectors, stack pointers, blah, blah, blah. And when you use this thing they call like hardware task switching, you basically like the CPU will load the TSS for that task and just start, like it'll automatically handle like reloading the stack, reloading the registers, etc., etc. And everything that I read was saying that I need one. But in this section about interrupt handling, hold on, let's see if I can find it. Give me a sec, Right, okay. So is this yeah, okay. So if we're going to be changing privilege levels, we find the handler stack and registers and stuff from the TSS, or we like save stuff to the TSS. And then we like switch to our interrupt context, switch back, and we can reload. But in no privilege change, we just write all this to the stack. So I think we might be able to get away without a TSS segment, even though that everything I read said that we need one. So I'm gonna try to like see if that works first, and then if it doesn't, then we can move on to try and implement it. So we are not going to be a system segment. All right. Executable bit. So here we will set this to 1 for one of them and 0 for the others. And direction bit. For data selectors, if clear segment grows up, if it grows down, offset has to be greater than limit. If for code selectors, if clear, this can only be executed from a ring set in DPL. If one code in the segment can be executable for equal or lower privilege level. Okay. Sure, readable, writable bit. For code segments, readable bit. If clear, read access for the segment is not allowed. If set, read access is allowed. Write access is never allowed for code segments. For data segments, writable bit. If clear, write access for the segment is... So for data, we set this to 1. For code, 1, I guess. It's kind of weird. Why wouldn't you want code to be readable? I would assume that code has to be readable. But I guess if you're like, maybe the CPU handles it all for you and you don't actually ever need to self-inspect your own code, that seems kind of reasonable. Access bit. The CPU will set this when the segment is accessed unless set to 1 in advance. And this means in case the GDT descriptor is stored in read-only pages and this bit is set to 0, the CPU trying to set this bit will trigger a page fault. Best left to 1 unless otherwise needed. Okay. So that actually doesn't seem too complex. And I guess we just start going at it. Oh, the other thing I wanted to understand in advance is what are these like where is this? CS, SS, GS, FS, ES, DS. Like, what are these? CS register x86. You can do it. What is the purpose of the CS register? Physical address is calculated. Segment address and offset address. The CS code segment register is used to address the code segment of the memory. Okay. What else were these? This was the SS register. Stack segment register. Stack pointer register. I see. So probably, I guess I just have to set that. What about, like, let's see the other ones. Like, what is the GS register? Or are these defined in the Intel manual somewhere? Let's see. Can I just look up SS? Oh, that's going to take forever to search. Let's see. Is one of these instruction format, instruction set? Can I see like registers somewhere? Basic architecture. No. Data types, instruction set, procedure. I'm looking for like register definition somewhere. But I don't really see it. System programming for instruction set extensions. Yeah, that sucks. SS register Intel manual. Maybe they'll tell me. Somebody will tell me what chapter it's in. Nope. 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 Okay. Well, maybe this guy will tell me where these guys are set. Aha! Here we go. This is what I was looking for. The x86 line of computers have 6 segment registers. CS, DS, ES, FS, GS, SS. That's exactly what I was looking for. They are totally independent of one another. Code, data, stack, extra, general purpose. So I guess I just point these all to the... What is extra segment? Where extra? Extra segment x86. Aha, aha, this is what I was looking for. Not what I was looking for. ES, or extra segment. Aha, in both real projection modes, the system uses 16-bit segment registers. Cool. The registers CS, DS, SS, and ES point to the current code, data stack, and one extra segment, determined by the programmer. So I guess I just don't care. FS and GS, no specific uses called by hardware. So maybe ES, FS, and GS are useful in some way for like kernel programmers. Maybe I want to like have like memory in some area for some purpose, and I want to be able to check that from... I don't know, I don't understand why I wouldn't just like stick that in RAM. Because like I would think that the point of these registers is for like automatic hardware, like offsets and stuff. Okay. Let's see if we can see like what is register ES for. Maybe somebody will tell me. x86 registers, ES. Here we go, ES, EDI. Used destination index, used for string, memory, array, copying, setting, and far pointer. These are extra segment registers available for pointer addressing like video memory. Ah! Aha! I don't really understand they'd be used, but ES register example. How does it use the ES register? In all other cases, ES is only used explicitly requested with a segment override prefix. Modern 32-bit operating systems apply flat memory model and blur this CPU peculiarity. Nevertheless, it remains identical. All right. Okay. So we'll just ignore it for now. And maybe we'll just set them all to be the same, like multi-boot does. Okay. So let's maybe start by pulling out these CS and SS. And if we understand correctly, they point to a code segment, which means that if we like look at the value in that register and then look at the memory that it's pointing to, we should get some form of table that resembles this guy. And we can probably validate by looking at like seeing if we can decode the base and limit addresses, because we know that that format is, we know what they should be when we come out of multi-boot. And we also know what they should be, what they should look like here. So we can like start by parsing this, and then once we have like a way, once we know we're parsing it correctly, we can like encode and test that our parsing gives back the same value that we wrote. I think I like that. So let's pop open main, where all work is done. And let's just enable this exit again. And I guess we have to write a function that pulls the address out of the DS register or the CS register. Let's start there. So this is going to be a function that's like read CS reg, and this is going to return a this is going to be like a U64, right? Because this is 64 bits. And this is going to use inline assembly, which I think is like this. Something like this. How do I do? Here we go. Raw string. And this is going to do output to a register and into ret. So we go like this. We say, please run some assembly that's going to, how does this work? I can't remember. Inline assembly rust. Okay, so where's an example? Temp equals out reg. Oh, but I don't need to do that when I'm working with registers directly. That's okay. So I guess we just say ret equals out reg ret. Consider returning the local binding. Yep. And I think I don't need to do this. I guess I do. So here I use HT syntax because that's what I used in the first example that I pulled from the OSDev wiki, and so now I'm stuck using it forever. Then I just load the value in CS. So move CS, and this goes source destination. So I guess I should call it like this. And here we also need to use the ASM macro. And then we need to make this function unsafe. Or do we claim that it is safe? I think we can claim it's safe. So here we just do this. And let's see what we get. So first, I guess we should double check what assembly is generated by this when we build it, because I'm not really confident. So if I go to target debug, I can objdump -d kernel. Oh. Last time I typed this, it was from this directory, and I can look for read csreg, probably. Maybe since it's not used, it's not linked. Maybe I need to, let's just put in these like attributes that say this is a C function, because that means that I will be confident that I can find it in the disassembly. So let's build again. And what did I call it? Read CS. Maybe it's optimized out because it's not used. So let's just say print line, and this is gonna do a debug render of read CS reg like this. So we build, could not compile. What doesn't it like? Undefined reference to EAX. Oh, I need to put this in here probably. Yep, okay, objdump and read CS reg. Oh, this is the wrong, I need disassembly. Read CS reg. Okay, so what does this look like? He pushes EX to the stack, he moves CS into EAX. Then he does some moves EAX into the stack, then moves it back. This seems useless, but whatever. And then he pops ECX. Turn. Very strange. I don't understand. Yeah, I don't understand. Let's just say we'll force AX here and see if this generates something different. So here we'll specify EAX manually. Build it again. And check and see what we see. So read CS reg. This does just look the same, so... Oh, maybe ECX is where it's used in the parent, and so that's why or something. Anyways, it doesn't look crazy, so let's just kind of see if we get something reasonable out of there. So let's print line debug print the pointer, so read CS reg. Cargo build. Oops. I forgot to put the % in front of this again. And let's cargo run and see if it works correctly. And we get an 8 here. Oh, this is the pointer to 8. And so let's dereference this. And we get this shit show of a number. So let's see if it looks valid. So what we should expect, what we should see is we should see a limit that is all Fs, probably offset 0. So let's make a function print CS or print segment, print GDD segment. Yeah, I like that. And here we'll take in a U64. And we'll call it segment. And nothing fancy is going to happen here. Right now, we're just going to print it as hex. And we pass in the segment. And then we call it down here. Read csreg. This. And now we should see that print again. Okay. So we do see, what we can already see here is at bytes, bits. What is this? 4, 8, 12, 16. We see some zeros, which maybe is what we expect here. Let's find it. So zeros at 16 for 3 nibbles. So that's 16 plus 12 is only 28. We expect to see it for 4 nibbles, right? We should see it 16 to 32. So there's a chance that this is coming in too late. So let's double check that the value we get here is the same if we pass it in to the kernel from start. So here, let's just immediately say, this is the multi-boot info. And now we can say move CS into EAX and push EAX, which means that we should actually get a third argument here, which is the CS reg adder. And this is a const u64. And let's compare that the CS reg adder is the same as read CS reg. Cargo run. Okay, so that is working as expected. Yeah, so this assertion passes. Which means that we do in fact have the right address, but maybe the table isn't valid. Let's just see for now. Okay, so first we need to extract the limit. So the limit is bits 0 to 15, so 0xFF. Right, is that right? 8. Or maybe it's like this. Is this correct? 4, 8, 12, 16. I think that's right. 1, 2, 3, 4, 1, 2, 3, 4. Yeah. So this is this. And then we have 42 bytes, or sorry, 16 bytes? 16 bits, which is 2 bytes of base. Then we have one more byte. 32 to 48 is, oh, that's, sorry, 2 more bytes. Can I fucking separate this somehow? Can I just put spaces in here? How do I separate long hex number? Separate long hex number in Rust. Oh, with underscores, maybe. Yeah. And here we have 6, how do I say this? 48, 49, 50, 51. So this is 4 bits, 52, 53, 54, 55, 4 bits. Okay, so we just need F here and like this. So this is this the right length? This is 1, 2, 3, 4, 5, 6, 7, 8 bytes. All right. Oh, I wonder if there's something messed up about like the storage format here. But we'll see. Okay, so this is the, how do I say what this is? This is the limit mask. So let limit equals segment and limit mask. Or I guess we should say limit lower and limit mask upper here, like this. And here we do not include this F, and here we do not include the bottom Fs. And these types should be U64. So this is like this. And actually, that's reasonable. And then limit is now the limit or segment and limit mask upper shifted right by what is this? This is 16 times 3. Which I should know off the top of my head. 16 times 3, that's 48. And we return limit. Our print line limit is the limit. And we want to print this in hex. And it's definitely not what we expect. Right? Because multi-boot says that this must be a 32-bit read-write data segment with an offset of 0 and a limit of FF. Side note. 1, 2, 3. That's not enough, right? Am I crazy? That the limit is not big enough to fit that number? Right? Because this is 4 Fs, and this is 1 more F. So that's only 5 possible Fs. F. Well, let's see if the base gives us 0. This could also just be wrong, by the way. Let's see. One, two, 3, 4, 5, 6. So there are a lot of Fs and there are a lot of zeros in here. Oh, I guess it would be interesting to see what the GDTR register is anyways. So we'll call this. Oh, wait, no, we can. So let's assume that this is entry 1 because it's at 8 bytes total. And so maybe if we read this next, if we read the DS register, maybe we should see an address that's 8 bytes higher. That seems reasonable. Print line. So we'll put read CS reg here and read DS reg here. Okay, so that's working as expected. And probably if we look at the GDT, like where the table is, the table should probably be at 0 because they're talking about how you need 1 null descriptor followed by, let's see. Here you need a null descriptor followed by entry 1 followed by entry 2. So we know that we're seeing entry 1 and entry 2 are at 8 and 16 bytes offset. So the thing at 0 should be the null descriptor. Oh, I wonder if we move 0 into ret and we call this read null descriptor. Hopefully we see null. So let's print line null descriptor. I think a seg fault shouldn't happen here, even though we're dereferencing null. Because we have no like seg fault protection on. So we'll call this read null descriptor. And we'll dereference it. Okay, it doesn't like that, turns out. Okay. That's okay. That's okay. So they have the null descriptor at 0. We can't read it. But maybe I would like to be able to make sense of what's in here. Is it fair to say that even though the segment register is set up and described before, the GDTR may be invalid? So the claim here is that these are in fact valid. And I wonder if like we're clobbering them by mistake here. it would be nice to be able to disable this allocator and get some info out of it beforehand. I wonder how we can do that. Port manager, we can just disable the checking like this. Right? Which means that it won't depend on the alloc crate or the allocator implementation, which means that we can move port manager before allocator and we can disable this stuff. Nice. Okay. Yeah. Okay. So now what would be nice is if we could see if the content of this is the same, and it looks like it is, right? This limit value is still coming out as not what we'd expect. Something we should think about is if, how do I say this? A 64-bit int is giving me the same layout as two 32-bit ints in series. Because I'm kind of assuming one 64-bit int ends up being like one big little Indian number. But I wonder if that's not how it's treated. So let's look at this again. And these are the offsets from the segment descriptor. So if we, instead of returning one uint64, maybe we return two uint32s in series. All right, so here we take in u32 2. And, or I guess we'll say const u32. And here, let's just see what we get. Can we do maybe a print hex, then print hex again, and we'll print star segment at first to get the first byte. Then we want to print the second byte after, so we can do star segment add 1. And this is actually backwards. We want to see that this is the same as what we were seeing before. Okay, so he doesn't like that because I dereferenced. So let's see this. And the question is if this number is what we're seeing up here. 2C3 at the end, yup. And F000F at the beginning. Yes, it is. Okay. So let's continue on and try parsing out the base and see if we see something different there. So we can undo these changes. We know that like the U64 is in the format we is like one big little Indian number. That's a confusing way to say that. And we know that this like allocation isn't adjusting that value at all. And now let's try parsing the base. So let's factor this out into like parse limit from a segment like this. These guys go here. We're not sure if they're right. And we say let limit equals parse limit. Then we need a new function to parse the base. So function parse base segment u64. And the base comes in. Oh, hold on. This was stupid. This should have been, okay, so I shifted it right by 48 to get this byte in this position here at the end, but really I wanted it in this position, so I actually should have left by 32. And let's actually see if that gives me something more expected. Somehow the same number? How's that possible? Oh, because this byte is 0. Okay. Let's try parsing the base. So let mute base equals segment shifted left by 16 and 0xFFFF for the bottom 16 bits. Then, oh, this is still wrong. This should be, oh, this is so stupid. This had to be, oh my gosh. This is segment and limit mask upper. Shifted the whole thing shifted left by 3. Before I was shifting only the mask, but I actually only want to shift the, I want to shift the whole thing together. So let's see what that says. Still exactly what we had before. Okay. But at least I am more confident that's correct. Okay, so okay, so this is like this. Maybe for consistency, we'll do this like we did up there. So we have segment ended with, right? So this is the first 16 bits zeroed out and the second 16 bits add together. And actually we have the next up to 40. So this is 32 plus 8. So we actually have FF like this. And then base or equals the segment and this is one, is this one whole byte here? 56 to 64, yeah. So this is FF 000000. We need, there we go. We need to mask off all of that, and then we need to shift that left by 64 minus 8, which is 56. No. Because we want this to become 56 minus 8, 16, 24. So, whatever. Let's punch it in like that. And we return base. And we see what this guy comes out to. Here we go. We print the base. Okay, so the base also is just not at all what we expect. Very cool. Very cool, very cool, very cool, very cool. For more information, see segment descriptors. So there's two theories here. One is that I'm reading it wrong, and two is that it's just invalid for me to read this right now. I wonder if there is an example of a like normal value. Very cool. Oh, this null descriptor, that's pretty funny. I guess this is what causes segmentation faults. And we actually can't read it because it's at the segmentation. That's so funny. Yeah, I really like some sort of like way to confirm if I'm using this correctly. And so I was really hoping that like reading the values that come out of there would help. And like we do kind of see, so if we do in fact see a 32-bit read execute code segment with an offset of 0 and a limit of FFFF, we should at least see 1, 2, 3, 4 zeros in here. And we actually do we? So 1, 2, 3. No, that's actually correct. Incorrect. This should be 4 zeros here, 5, 6, 7, 8. We should see 8 zeros. 1, 2, 3, 4, 5, 6. So we're not seeing that, which is very... that means that we must not be reading this correctly, or we must not understand the format correctly. Let's just like double check that that's right. So here this is 16 to 32, 16 to 40, right? Well, let's pull out the calculator. And by calculator, I mean this. So this is 16 minus 40 minus 16 plus 63 minus 50, 64 minus 56. You can read the address of the descriptor table using SGDT from assembly instruction. I don't think the values in the segment selectors are actually pointers. Oh, interesting. Oh, are they segment? Then what are they? That's a good point. Thank you. Thank you, thank you. Because I've been struggling. So you're arguing that these are code segments defined as segment selectors? Maybe? So the problem is I was hoping that I could get something out of here without reading the GDT, because the GDT register is not guaranteed to be correct. And so I was like really just hoping that there was like some way for me to like validate that what I'm doing, like the parsing in advance. But maybe you're right. So let's see if I can prove this somewhere. So CS register OSDev wiki. Segments, blah blah blah. 6 segment registers that are totally independent are used to form addresses. Oh, I see. So you think the 0x8 that I'm seeing here is an offset into the GDTR. That seems reasonable. Or sorry, the GDT table, which is an address at GDTR, I think. Well, we could also just hope for the best here. They say that GDTR may be invalid, but maybe it's not. So let's look at that SGDT command. Store global in the destination operand. Okay. Sure, yeah, let's try that. Let's try that. So let's call this read SGDT or read GDT R. And this is going to return a const U32. And here we take SGDT and we store it in ret. And we hope that this works. Yeah, so this, now we think that these are just offsets. So we'll call this a U32, we'll call this a U32, and we'll load the GDT. So I think it's, what do we call this? Read GDTR. And we'll debug print this. And this isn't like this anymore. And we'll just not call this print right now because it's broken. Use of unknown instruction mnemonic. The size of it. So let's look at SGDT new assembly. Is it like encoded in the opcode or something? What doesn't it like? SGDT %0. Okay, so what doesn't it like about that? Use of without size suffix. SGDT. Stores the content, blah, blah, blah. In legacy compatibility, 6-byte memory location. In 64-bit mode, the operand has 8 plus 2 bytes. Okay. So I guess I need to size ret here. So I can just say that this is a U32 or something. In legacy or compatible specifies a memory location. Am I crazy? Destination operand specifies a memory location. Yeah, maybe that's good reading. Yeah, you're right. Okay. Yeah. So here I can say, I can probably pass this in as a pointer. Probably. So in Rust assembly, do I have that open somewhere? Here we go. Can I specify an output of type memory? Memory. Inline assembly. Oh my gosh, I jumped around. Okay. So I can... in, out, laid out, in, out. So I guess I can put the memory address that I want to store it in a register. No. How do I get just like memory address into my inline assembly? Oi, oi, oi. Oi, oi, oi. So let's read this again. Yeah, that makes sense. Rust inline assembly memory operand or something. I guess maybe I just have to read this more closely. Inputs and outputs. Move, that's an example. Still doing register, register. Registers, registers, registers. I want to see someone just like write some shit into memory directly. But none of these guys are. Ooh, what's this? Inout reg? Nope. Ah. What's going on here? You can wrap inputs and indicate that are memory operands. Okay. That seems reasonable. So here this is using Intel assembly syntax, but what about AT&T? I guess I just won't use AT&T for this. So here I can do this. This is a U32. And we'll return it as a pointer. And then here I just need to specify that this is an input register. And like this. There's no argument named ret. There we go. Ret isn't initialized, so we set this to 0 in advance. And we probably put a mutable here. And this is probably an in-out, actually. Cannot use value types for inline assembly, only integers, floats. Okay. Let's just see if this does anything. So let's see what we get when we run that. It doesn't like that. Unknown token and expression. Instantiated into assembly here. Oh, because I have that % sign on still, so it should actually be like this. And maybe it didn't like that. No, it does not. Okay, cannot use value of type U32 for inside assembly. Or for inline assembly. Only integers, floats, pointers, and function pointers. This is a pointer though. Maybe I have to cast this. as mute u32. Invalid ASM cannot assign to this expression. So what if I make this a pointer to mute ret as mute u32? So, and then pass in this pointer as my argument. And this can't be right. Right? This can't be what I'm supposed to do. But it does like that better. This doesn't make sense to me. So I pass in... Shouldn't this be the same? That's not a bad idea. Stealing the implementation for the x86-64 crate. Yeah. I like that. I didn't want to cheat, but you're right that I am stuck. Okay, let's clone this guy and take a quick little peek inside. So we'll go here, we'll clone it to this guy. We'll go in here and we'll grep for sgdt. Okay, that was close. So I guess this is close to what I had before. So here I should be able to... They're claiming that this is an input, even though I'm using it as an output. And they're also saying I need options, no stack, preserves, flags. Oopsies. Preserves, flags. Okay. And cargo run. So what I'm confused about is why this fails so horribly. Let's try not casting this. Let's just point this as a U32. Still nada. Still nada. This is very odd to me. Maybe it's because I put it in brackets. Named argument is never again used. Oh. Okay. And it still doesn't like that. This looks like pretty much exactly the same as what they have. I don't understand why it worked when I stuck it behind a pointer. That's really odd. Maybe this needs to be a larger... what is their size, their descriptor table? Okay. Okay, so this works if it's a U64 but not a U32. I was under the impression that because I'm running in x86 that my addresses would be U32s, but I guess not. So maybe let's double check what SGT means. Maybe I'm confused and this should be how do I say this? I guess I'm trying to understand why it's a U64. So where was I? I was looking at the sggt command, which was probably in this one. sggt. And stores the global descriptor table register in the destination operand. The destination operand specifies a memory location. Okay. In legacy or compatibility mode, the destination operand is a 6-byte memory location. If the operand size attribute is 16 or 32 bits, the 16-bit limit field, blah, blah, blah. In 64-bit mode, the size is fixed at 8 plus 2 bytes. I'm in protected mode, though, I think. Not legacy or compatibility. If the operand size is 16 or 32 bits, what is operand size attribute? The 16-bit limit field. Okay, well, SGT is useful only by operating system software, however, we're going to be using blah, blah, blah. If operand size is 16 or operand size is 32. This is weird too, actually. This is not what I thought I would be getting out of here, because this is just getting the limit and the base directly. But that means that I'm not getting like the full... Oh, I see. Oh, am I high that the limit and the base need to come in together, and like the base needs to be a 32-bit address, so I need extra room. I need 48 bits. That would make sense. How do they know the size? That I don't really understand. Instruction operand encoding. Operation M mod. I don't know what this means. I'm not going to pretend I do. Let's look at the disassembly and see if that helps me at all. Aha! So the assembler is automatically appending an like a long here, SGDTL. What does that mean? SGDTL x86. I see. So there's like I have to shove something at the end, and I don't really know what the L means or how to figure it out. So let's just pretend that this gives me something and see if we can parse it in some way. Oopsies. Did I have... Was I reading the wrong example? No, okay, so this is what I was doing before. And this just takes a limit and base. And what does this look like? I can't jump to reference in here, so I'm just going to leave it. I'm just going to leave it. Okay, so let's try now looking at that. So if the null descriptor is all zeros, we probably have like a good indication that this is working correctly. So let's try that. We'll read the GDTR and then let's just dereference it and see what it looks like. So we'll pretend that the GDTR is returning a const U64, and then we'll dereference it and we should see a bunch of zeros. Because that's like the first offset, I think. Come on, baby. And we just return ret as const U64. And that doesn't work. Right, because I want like the first 32 bits of this. So ret as U32 as const U64 or something. Nope, doesn't like that either. Okay. Well, we were close. Oops. Okay, so we're back to printing a number. And is this like a reasonable number? Who knows? I wouldn't expect it to be there. It also says that GDTR is probably invalid, so I should probably like trust that. So I guess, unfortunately, maybe we just have to start going into like implementation of writing this thing without being able to probe it to understand what to do. So we'll just say that this attempt failed. And let's just start writing into it and see if we can understand. That sucks. I was really hoping that that was like going to get me somewhere. Give me like a good intermediate checkpoint. But that's okay. So next up is let's just program the GDT and just hope for the best. So we have these segment descriptors. And we know ish what we want. I wonder maybe there's some library somewhere that I can generate segment descriptors with. Look at their value, and then I can test my parsing based off that. And then I can use that as an intermediate checkpoint. So maybe there's like Python library to generate GDT. Or maybe there's like generate GDT segment online. Is there like some service that does that? No. But the OS Dev wiki did have this. So maybe what I'll do is I'll copy paste this guy into its little C program, and let's just print out the created descriptor. So, oh, nice, and I don't even have to do anything here. This actually does what I want. So let's say that I want a base, a limit of 0xff 1 2 3 4, and a flag of 0. We can gcc-show test.c. We output as test, and then we run test. And then we can make some, then we can start parsing this with the parser, and then we can validate in Rust. Okay, I like that. So now we're starting to get into the territory where maybe we just want like a source GDT rs. And we'll move, I guess there's nothing really in here. Oh, here we go. Parse base and parse limit. We'll move these into GDT rs. Like this. We'll include this here. And then we will, let's see, create some tests here. So we make a test module, and we use my testing crate, as well as use superstar. And we can now create a test that tests base extraction. Like this. And this compiles. So now we have this descriptor that we generated. And actually, let's generate something a little bit more intelligent. So our base will be 0x1 2 3 4 5 6 7 8. And our limit will be dead beef. And between those two, we should get a unit or unique. Oh no. I just overwrote my source file. No, I have to copy paste this again. Thank God it wasn't something more important. Okay. So this time we're going to do 0, 1, 2, 3, 4, 5, 6, 7, 8. Dead beef. gcc-o test.c. Run test. Now I have my base should be 1, 2, 3, 4, 5, 6, and 8. My limit should be dead beef. And if I go into my GDT test, I can now just say, we can say const test segment equals this. And this is a U64. And we'll test parsing this. So we want parse base of the segment to be 1, 2, 3, 4, 5, 6, 7, 8. And we want the limit to be dead beef. And now we run cargo test. It doesn't like that because these need to be as U64s. And try again. Okay, nice. So we've already proven that there's a bug here, which is great. So our base parsing, what's it look like if I go like this? Can I print these as hex? Let's do that. So we'll just manually print this out like this. And this is 3, 4, 5, 6, 7, 8. Oh, are these fucking things not in order? There's no way, right? Where is this? GDT segments. Base 0 to 15, base 16 to 23, base 24 to 31. Yeah, so it should be 1, 2, 3, 4. Oh, these are the highest bits though. So that makes sense. So what did I get there? I got 3, 4, 5, 6, 7, 8, which is expected. And so cargo test. Here I'm getting 1, 2, 3, 4, 5, 6, 7, 8. Oh, and it's the limit that parsing that's broken. So my limit parsing what do I get here? Almost. I'm missing an EAD. 1, 2, 3, 4. Oh, because the limit parser can only be 20 bytes. Or 20 bits, I should say. So that's actually correct. Okay. Sweet. Sweet, sweet, sweet. Okay, so we know that these functions that we wrote earlier to parse are correct. We're chilling. Which means that now we can start writing like this. We can start converting this like serialization function from C into Rust. Okay, so this is a function that takes in a base as a U32, a limit as a U32, and flag as a U16, and this will return a U64. And we'll say descriptor equals 0 to 64, or I guess we call this limit. And I guess we just do this here. Let mute descriptor equals limit and 0x f and this should be a U64. Limit needs to be limit doesn't need to be cast here, but this whole thing does. Here it doesn't like this, so we can do this. We have to do this again. And we have to do this. So these all have to be U64s to make Rust happy. This shift is okay. And then we have to do the same thing. Base as U64, shift to left by 16, limit as U64. Okay. Now we can do the back and forth test, where in here we say test back and forth maybe. And here we'll say base is x 1, 2, 3, 4, 5, 6, 7, 8. And our limit is sorry, base should be U32, limit should also be U32, and this should be dbeef as before. And then we say segment equals create descriptor base limit 0, and these should still pass. So let's see. Nice. Okay, so the back and forth serialization is working correctly. And now all we have to do is load some descriptors. It would be nice to be able to like set these flags with some words. So what do they do in test in the here? Jesus. So what about like access mode here? Access mode doesn't seem like it's handled by this at all, actually. I was hoping for more in this copy paste I found on the internet. Uh, maybe that's what this like data PL is. So what are they doing with the flags? Let's see. So they're just putting, they're considering flags is here. What about access byte? I guess they're just not setting the access byte. Unless they're considering this access byte. F0, FF, 00. What the fuck is that? What the fuck? F0, FF, 00. So I guess it's this. Where did I go? I was here. F0, FF, 00. And then they shift this left by 32. Okay, so they're considering flags to be the limit, sorry, not the limit, the flags and access byte combined, which means that if I just set my access byte, this is so much work. Okay, so present bit allows an entry to refer to a valid segment. Must be set 1 for any valid segment. Okay, so we'll start with that. We will start with that. Maybe I'll do like the Rust thing here and make a like access byte builder that has my like access byte. Is it 1 byte? I can't remember already. Yes. And here we'll implement it and say function set present return self, and here we'll do self access byte or equals 1. I guess I have to set the value, so enable true, or sorry, not true, bool. And this will be like if enable, we shift this by 7. 1 shifted left by 1, 2, 3, 4, 5, 6, 7. Yep. And self.access byte or equals this. Else this is an and equals 1 shift. No. This is a inverted 0 shifted by 7. Nope. Inverted 1 shifted by 7. And then we return access byte or self. Bitwise not is an exclamation point. Okay, and we need to make this mutable. And now we need to abstract this function and test the bit set. So let's do that. So we have function set bit input is a U8, and we don't want to call this set bit. We want to call this we call this an enable is a bool, and bit is a U8 again, I guess, and it returns a U8. And we just cut paste this logic up here. And this just shifts to the left now by bit. And input is mutable now. We replace these with input. And we return input. Okay. So now we can say set bit self access byte enable 7. This. Okay. Now we can test this set bit function. Oh, oops, why am I in main again? I want it to be in GDT. So we'll cut paste this all out to GDT. Put this guy here. Yeah, and then we can create test set bit like this. And let's just say that like our start. Oh, what am I doing? This input is, oh, it is actually what U8. Okay. So start U8 equals like this. We're starting with a fully set thing, and we want like set bit start false at bit, I don't know, 3, 4. So now this should be 0xF7, I think, because I'm disabling the fourth one, I think, if my hex is correct. So this should be 0xF7. And we return okay. Cargo test. And we do not get that right. Let's just double check this. Oh, that's because I shifted it by 4, not 3. Nice. Okay. So this clearing is working correctly, and so we'll call this test clear bit instead of set. And we'll call it set, so we'll do the same, and this should now be like this. True. Okay. Cool. Okay. So now we're confident that we can like test the set bits, and now we can start using this like access byte builder to start setting these values. So present bit will always want to be 1. Present bit. DPL is always going to be 0 for now, but that's okay. So we'll say value is a U8 that gets taken this time, and we'll do the same thing where we set the bit, but we're going to set it twice. And we have bit 6 and bit 5. 6 is val shifted left by 1. And there's 1. Bit 5 is val 0x1. No shift. So just ANDed. Arguments of this function are incorrect. Oh my gosh, so much casting. This arguments of this function. Oh, oops. So this shift left 1 by 1 and 0x1 is equal to 1. And we need to like make sure our brackets are right, and this is also equal to 1. Okay. Okay. Now we need to set this S bit. Descriptor type bit. I guess we can just call this set S. Itself, enable is a bool again, return self. And this is like this again. But instead of 7, this is 4. S is 4. We have set E, which is bit 3. We have set DC, which is bit 2. And RW, which is bit 1. And A, which is bit 0. Okay. Our default state is 0, I guess. So we'll say access byte builder, access byte is 0. And let's see where this goes. So now we actually have to like create this thing. So I guess here somewhere, let's just call like test access byte, and let's say access byte equals access byte builder new, and we'll set p to be true. They always want p. DPL should be 0. Descriptor, so if clear, the descriptor is a system segment, otherwise it's a coder data, so we'll set S to be 1. E is 0 if it's a data, 1 if it's a code, so we'll say E is 1 as well, or these should be true, I guess. Set E. DC is direction bit, so for code selectors, this can only be executed from the rings of the DPL, so we probably want that. So set DC, what was it? Set true. Oh no, we want this to be clear, sorry, false. And we'll set our W to be if clear, read access for the segment is not allowed. If set, read access allowed. Let's clear it for now. And access bit, it says best left to 1. And now we just test that the access byte, I guess we call build at the end. Is this how like the builder pattern works? This takes itself and returns a U8. Self.access byte. So we test that this is 100110001. Cargo test. Do I not have a set? Oh, set present I called it. Let's just call set P. Very nice. Okay, that's working as expected. So we'll call this test access byte code segment. And what goes in the flags again? Bump, 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 bump. Flags. Access byte flags. Granularity flag. DB size flag. Okay. And long mode flag. So this should be, we'll just set the flags by hand right now. This is 0B 1100, I guess. Okay, so now we can probably like start creating like our initialize, like our public function here, which is gonna be called by name. So we can just say init. We're just gonna init the descriptor table, and we're going to use this code segment. And we're gonna make this a U16 because of the way that this create descriptor is set up. And so, let's think. Let flags equal 0B1100, I think is what we said. Yep. And we'll call this E16. And this should be shifted left by 12, I think. Because this flags is set at access byte is 4, 8, 12. Yeah. And now we say let flags equals flags or access byte, like this, as U16. And now we can create a descriptor. So we now create our descriptor. And let's see. Base is 0. Limit is 0xFF or something. Flag is flags. And we'll call this the code descriptor. Okay. Now we need a data descriptor, which is the same, but we'll want to do a different set of things here. So let's run back through these. DPL, call this. This is the same. This is the same. This is still coder data. E we need to set to false because this is a data segment. DC. Here we want clear probably. RW we want it to be read write. And X axis should be 1. So this is the same now. And so now we have a code descriptor and a data descriptor. And we need a null descriptor, which is just 0. So I think probably we can just stick this in static memory and then load that static memory into the GDT register. That seems reasonable. So here we'll just say static GDT equals is a 3 U64s in a row. 1 for null descriptor, 1 for data, 1 for code. And this will be initially. Ooh, I wonder if these can all be const functions actually. And then I can just call this directly here. Let's see. Set bit. This can also be a const function. Wow, this is cool. I didn't think this would actually work. Multiple associated items are never used. Wow, I really didn't think. Okay, cool. So now, get GDT vals, and this can be return a U83 or U64 3 U64s, and then we just return 0 U64 code data. Am I crazy? Is this really all it takes? And then here we can say get GDT vals. Hold on. Here we go. Double equals in here. And then all we have to do is on init, all we have to do is load it. So let adder equals the address of GDT. And here we're going to call store the GDT, right? Like this. So we're going to say sGDT or lGDT. And we're going to do the same using the memory trick like we had before. We're going to load the GDT from this address. And this address is and GDT. So we can just say in reg and GDT like this. And here we need to use core arch ASM. And here we need a comma. And this needs unsafe. Okay. And then main, we can just say print line or GDT init. And now we should hum. I think that we're missing some rules on how to load the GDT, actually. Because I think that it's not just... Oh, maybe this is all it needs. So, shouldn't CS be updated? Aha. So here, I also need to set all of my registers to match. So CS is 0x08, but let's not get ahead of ourselves. Let's see if this crashes first, just for interest's sake. No. Okay. And we say here is our GDT. It's at 0x0 now. That's not good. Because here, we thought that we set it. LGDT x86. Loads the values in the source operand into the global table register. The interrupt table, blah, 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 blah. Contains the base address and the limit. So, are used only in operating system? Yeah, I get it. I'm an operating system. If the operating size is 16 bits, a 16-bit limit, and a 24-bit base address. Oh, I need a limit in here as well. So, let, what do I say this is? Val is right, so this is not the GDT. My GDT also needs a limit at the front. So we probably need like a struct GDT. And this is a packed C struct so that everything gets lined up the way I want. Limit is a U16, I think they said. 16. Yep. And then GDT is a U64. 3 for now. What is the limit of my GDT? So this is the table. And here I need size bits 0 to 15, offset bit. Yeah, okay. 16 to 48. Okay. So that's not actually one out here. So this is fine. And now I just, in my init, I create a new thing. So I'll call this GDT entries. I'll say limit equals GDT entries len times, I guess I can just say core mem size of can I get like the size of a variable instead of a type? Rust size of variable. Size of val. And this is GDT. GDT entries, sorry, then I guess the limit is size of the table in bytes subtracted by 1. The subtraction because, sure, so -1. Oh, this is fucked. Oh yeah, that's right. Okay. Size of val, it takes it in by reference, so it's a okay. Print line limit. Let's just double check this. Cargo run. So this is 23, which is as I expect. 8 times 3 minus 1. Good. Now we say that the with the GDT. Oh, does this need to point to a valid point in memory? It actually does. So that means that not the physical address. I see. So I have a GDT. This is the tables. The table. And then I also have the register. And do I have to load the register with a memory address? I would think no. So let's see what happens if I do this. We specify in reg GDT. And GDT is the location of the entries shifted left by let's call this as U64 shifted left by 16 or the limit. Is that right? Limit, yeah. And this is limit as U64. Const U64. Can I do this? Oh, there we go. Okay. And I cannot pass in this. Aha. So this needs to be loaded as memory because the size of it is bigger than what can fit in a register. So that makes sense. So I very much hope that this is not still accessed after. So let's see what happens. So now we get a GDT that is this. And let's also print the value of the GDT entries. Like this. Casted to a U64 pointer. The idea being that we should see something very similar. And we do here. 136C78, 136C78. So now we accidentally loaded something invalid before. And that didn't work. That just was 0. And now we've like constructed a GDT and loaded it, and it sure is these numbers are matching, which means that maybe it loaded. And what would be interesting is like if we can prove that this is working in some way. But this has been like a lot of bit manipulation. And I've been going for a while, and my head hurts. So I think I'm going to call it there for today. Yeah, apologies for not getting as far as I wanted to. We'll continue this tomorrow and hopefully get a little farther. Thanks for watching. Catch you on the next one. Bye.